Hello, today we're going to talk about complex I and J. To start with, we're going to talk about how numbers are represented in a one-dimension space. So, when you first learn number, you usually start with one-dimension numbers. So you start counting 0, 1, 2, 3, which is the natural numbers. Then you learn the negative numbers, -1, -2, etc. Um, and then you learn about more elaborate numbers, more complex, more how to say it, numbers that can't be defined properly. You learn about pi, which is a rational number, irrational number. Um, yeah, and you start building numbers, and then usually learn uh, the first dimension, which is essentially a line, which is R, represented by this letter here. Wait, can I zoom in, please? Okay, by this letter here, R, which represents the real, and this is pretty much what you do when you draw a line. But we'll consider here um, another um, group, which is another vectorial space. Yeah, a vectorial space, which is the complex number represented by this letter C, which is how to say it in English. It's a composition between one dimension of R and one dimension of IR, um, where I is a very special thingy mathematically speaking. So basically, you will start with a line, and then you'll add another line multiplied by I, and you'll start doing properties on it. Um, and yeah, that's pretty much what happens. So you can rewrite a complex z by saying that it's x plus I and y, where x is the real part and y the imaginary part. So you have two um, lines that represents the both the real part and the imaginary part. As I said earlier, is the z and the x and the y components. So we usually call it the complex plan. So at first we'll start representing few numbers. This is 1, 1, 1, 1. This is 1. 1 in like usually you'll see it, and then later there is 2, 2. Okay, but if you multiply by I, you'll find that if you multiply this by I, it will somehow manage to be circa here. This will be high. Then you can do better. You can rewrite your complex z. You can rewrite your complex z. Where am I? Yes, please. Okay. You can rewrite your complex z as being a times an exponent, yeah, I times an angle that usually called theta. Basically, what it means is that you take any line of length what, how did I call it? I called it a, of length a. So you put a, and the angle between the real part and this line will be called theta. Theta here, theta. Okay, so you'll have a point in space that is defined both by its real part and its imaginary part. There are a few interesting properties. Oh yeah, I forgot to say that it's a direct angle. Yeah, so you have a point in space that is defined by both its real part and imaginary part, and both by and also by its module, so the a part, and its angle, which is the argument. Okay, so this is actually very helpful for other things, such as electricity. But okay, this is kinda tricky. In physics, we don't use the letter I for complex representation of numbers. We'll use the letter J for a simple reason is that when you do, because this is mainly used for electricity stuff and for electromagneto-quantic things, that's kind of complex with waves. Okay, I'm not going to talk about it. Because you use intensity of few things in your system, usually intensity of the electricity that flows in your system. So you'll have the letter I, and if you have high, it's kind of complex, and usually you can find also the structure. Um, where is it? Where is it? Where is it? Where is it? High. It's not there. Oh yeah, this. You can find this high being equals to a plus ib, and it can be confusing. This underbar means that it's a complex, and usually you study its module, not its argument, unless you are doing theories of improving the, the power of output of your system. So you have you have representations like this, and using the same letter is weird. So we'll not use the letter I, but more J. Okay, I'm going to erase this. How can I do this? Can I do this like this? No. Okay, same. Okay. So you'll draw a basic. Uh, Wait, I'm not going to demonstrate it like this, but then you can do electricity. You can, well, I'm going to say that. If you have a sinusoid in terms of electromagneto-quantic waves, um, you can have things with the form A exponent I omega, well, no, J, sorry, J omega t minus kx. And you'll often find these kind of things. So when you'll derive this with time, there will be a j. If you derive it with time, if you derive it with time, if you derive it with time, you will find j omega a exponent the other thing. And if you derive by x, which is the space, you will happen to be minus kx, and you can do actually lots of calculus with that, with sine, cosine, with its complex writing. I'm not going to demonstrate it, but you can sum them. You can study how it works in few different conditions depending on what inputs in terms of frequency you input. You can see that few things happen. Resonance in French. Uh, yeah, it's very useful if you are doing electricity or electromagneto-quantic. Okay. Well, why did my screen capture? Oh yeah, what? Yeah, okay. I'm stupid. Yeah. So I was saying that you can cosine can be rewrote. Well, not cosine, but you can sometimes find things like this as an input for tension. You can find something like this, and when you'll derive it by time, you'll find j omega, and when you derive by space, you'll find, oh, not kx, minus ka exponent, the other thing. Also, then there is another problem. This J letter, it's actually something that is also used in other field, which is mathematics, because in math, J equals the okay J, how can I write it, is solution of x to the power of 3 equals 1. Okay, that's how you define J. Okay, so there are actually three trivial solutions for the equation x to the power 3 equal 1. That is the set of 1, because 1 times 1 times 1 equal 1. Exponents I 2 pi divided by 3, and exponent I 4 pi divided by 3, and I'm going to demonstrate it. Okay, so let's go back to the previous scheme. I can't remove anything. So imagine you want the solution something to the power 3 equals 1. So you want something so that when you apply it 3 times, you will come back to this, to the one, the real one, the one that is on the real axis. So when you put something to the exponent 3, it means that the module will be at exponent 3, but since it's 1, the only solution is that the module is 1, because if you put to the power 3 a positive, I forgot to say that the module A, when you write it like this, is always positive, not in physics but in math, is always positive. So you'll have the module must to the power 3 must be 1. So the only real positive solution is that A equals 1. Also J must, since it has the property that to the power 3 it must equals 1, it must has the property that the angle, when you apply it 3 times, it must come back here. So you have actually 3 solutions. The first solution is 1, like here. Oh shit, how do I do this? Okay, can I please do this? Stop selecting things. Okay. Okay, so 1, because when you apply the module, which is 1 times 1 times 1 equals 1, the angle is 0, so 0 plus 0 plus 0, it means 0 angle, so you don't rotate anything. The other solution is exponential I 2 pi divided by 3, which is this one, with the module being 1. So for the module it's 1, so 1 times 1 times 1 equals 1. For the angle you have this angle, I'm going to draw it with a small thingy. No, it's ugly. Can you see it? No. This one, this angle. So you'll have this angle. You want it to be, when you apply it again and again, you have to come back to 1. So you'll have this angle and this angle, and that will actually be a solution. The other solution is minus j, or j squared. It's the only one that has the property that minus j equals equals g squared. So it's this one here, this one. So it for the okay, it's badly drawn, so that is supposed to be the same length. It is supposed to have the property that to be solution of the equation x to the power 3 equals 1. So when the module is 1, so no problem. And for the angle, you have to apply another color, this angle, but you apply it. Yes, am I saying bullshit? No. You apply it again, so you'll come back here, and then you apply it a third time, and you come back to 1. So yeah, I just demonstrated that there are 3 solutions, which is this, and you can find that this one is actually, wait, yeah, this one is actually this one but squared, which is an interesting property, isn't it? There are many things you can do um, with complex, but not many with the third root of 1, which is j in math, not j in physics, because this is just pure math masturbating stuff, and this is actually more concrete. Well, technically not concrete, but what will happen is when you study electricity, you'll find that the I part remains to absorption and x to something that doesn't absorb anything, just using what's in it. So you will want to have more of this than this usually. It's kind of tricky, but yeah, it's very important. You can also use it to calculate um, uh, electron clouds around an atom. You can use it for mechanism studies. You can use it for pretty much everything that has either symmetry or a 2D space, because this will be helpful to solve everything that has angles and things like that. Other than that, in terms of mathematics, there are pretty interesting stuff to study. So yeah, um, I think that's all for complex. I hope you understand the difference between I, J, how to represent a complex, and thanks for watching. Bye.